This is a video over section 5.4, Special Systems. Section 1 was over solving systems by graphing. Section 2 was systems of equations solving by substitution. Section 3 was elimination. Section 4, Special Systems. We're not really going to learn any new method here. We just need to discuss a couple of unique situations. Okay, we're going to start with three types of answers. In sections 1, 2, and 3 with graphing, substitution, and elimination, all of our answers, there was just one solution. One solution. Okay, just one solution. What that looked like was we have a system of equations where we had that one point of intersection. One solution. Okay? But we have other different types of cases. We could talk about no solution. What happens with no solution? Remember what we're actually finding. When we're solving systems of equations, what we're looking for are where two lines cross. And if two lines cross, if two lines don't cross, that means they are parallel. They are not going to cross. Okay? The third situation we need to look at is the case of infinitely many solutions. Infinitely many solutions. Okay? If you were to look at it graphically, this is what you would see. You would see one line. If it's infinitely many solutions, that means it's the same line right on top of each other. There is no difference. Okay? So we have three different cases. We have one solution. That's what we've been working with so far in Chapter 5. But today we're going to look at the cases of no solution and infinitely many solutions. I want to be clear that infinitely many solutions is not quite the same as all real numbers, although it's very similar. Okay? Infinitely many solutions is a more accurate term than all real numbers. All real numbers says that you can pick any x and any y, and that would be a solution, which isn't quite right. Infinitely many solutions says we could put as many points on this line, here, as we want. We would never be able to count all of the solutions. That's why we use infinitely many, but all real numbers would imply that, oh, maybe this is a solution, or this one right here, or that one, or one over here, or here, or here. Okay? Not quite the same thing. So we don't want to use all real numbers because it's not technically all real numbers. Okay, so what does this look like? Well, let's do some examples here. Let's solve. Number 1, your first system, x plus y equals 3, and 2x plus 2y equals 6. Problem doesn't say which method we need to use, so we can choose whatever method we want. I like the elimination method the best, so I'm going to use elimination. If you want to use substitution, go right ahead. That is perfectly okay. All right, so I want my y's to be the same. I'm going to choose my y's to be the same. Okay, so if my y value here is 1, my other y value is 2. If I count by 1s and count by 2s, the first number they have in common is 2. So to get this y value to be 2, I need to multiply it by 2. For the other one, it's already 2. It doesn't need to change, so we'll go by 1. This is a 2, by the way. Let me see if I can erase that and maybe make that look a little better. That's a 2. Okay? So the top equation, multiplying everything by 2. So we'll have 2x plus 2y equals 6. The bottom equation, multiplying by 1. 2x plus 2y equals 6. Well, we have a conundrum here. It's the exact same line. So, if the two equations are exactly the same, we could still do, let me erase that. We could still do step 2 of the elimination method, add or subtract. Since we chose y's to be the same, the 2 and the 2, they're both positive. Same sign means subtract. So 2x minus 2x is 0. 2y minus 2y is 0. So the entire left side is down to 0. 6 minus 6 is equal to 0. Now, if we were just solving an equation with one variable, we would use all real numbers. But we're not using just one variable. We have two. Go back to your picture. We have the same line. 2x plus 2, whoops, I'm on the eraser here. 2x plus 2y equals 6. 2x plus 2y equals 6. It's the same line. With our picture, the same line means infinitely many solutions. So our answer here, you can write it one of two ways. You can actually write out, oops, infinitely many solutions. You can write it out in words, or the shorthand, IMS. Either one is totally fine. Number 2, let's take a look at another one here. X plus y equals 3, and x plus 2y equals 4. Again, I'm going to use elimination. I think elimination is the best way to do these problems. I don't need to do any multiplying for step 1 because I've got an x and I've got an x. The numbers are the same. And they have the same sign as well. They're both positive. So same sign means subtract. So we're going to subtract. X minus x is 0. Y minus 2y is negative 1y. 3 minus 4 is negative 1. So if I've got negative y equals negative 1, that means positive y would be positive 1. Just divide both sides by negative 1. Now for step 3, substitute this for that or that. It doesn't matter. I'm going to choose this one because I don't have to do any multiplying. So I'll have x plus my y value, which is 1, equals 3. This is a pretty simple algebra problem. X is equal to 2. So my answer here is 2, 1. Okay? I never ran out of variables, so I do have an answer. Your one answer is 2, 1. Your picture would look something like this first one right here. Okay? If I don't run out of variables, I'm going to have a solution. Alright, last one, number 3. Y equals negative x plus 3, and 2x plus 2y equals 4. Alright, I'm actually going to use substitution for this one because my y is already by itself. I don't need to do any rearranging. Excuse me. If y is already by itself, go ahead and substitute things in. So this, where y is equal to negative x plus 3, that's going right there in for that y. Okay? So 2x plus 2 times my y value. We know y is equal to negative x plus 3. And then that's equal to 4. It's the same problem now. Just distribute. 2x plus 2 times negative x. Actually, I'm going to erase that plus. 2 times negative x is negative 2x. 2 times 3 is 6, and it's equal to 4. 2x minus 2x is 0x, and 0 times x is 0. So really, these cancel out. I'm just left with 6 equals 4. Well, I'm out of variables, and I'm pretty sure that 6 is not equal to 4. So if you have something that is mismatched, like 6 equals 4, then your answer here is no solution. What this means is that these two lines are parallel. That's this one for number 3. Okay, the two lines are parallel. They'll never cross. And if they're never going to cross, they're never going to have a solution. Sorry, it's that one. Never going to have a solution. Now, so how do you know what the difference is? Okay, so if you get something in the end that looks like 0 equals 0, or 2 equals 2. I don't think that would happen, but it's possible. This one is IMS, infinitely many solutions. Okay? It means the two lines are the same. If you get something like the last problem where we had 6 equals 4, or you could have 0 equals 1, something like that, then it's no solution. Your picture is two parallel lines. That's what your picture looks like. The lines will never cross. If you don't run out of variables, if you get something like x equals 4, that is a solution. Okay? It's not going to be one of these two up here. If you still have an x or a y left, you have an answer. Okay? Your graph might look something like this, where the two lines do in fact cross right there. Okay? So just be very clear. If you have something that matches, infinitely many solutions. If it doesn't match, no solution. If you have a variable left, you have a solution.